You are welcome to the GMAT 41's Elementary Mathematics class. It's important to state that this course, Elementary Mathematics, is further mathematics. In this video, we want to look at the topic polynomial. Polynomial. What is a polynomial? Now, the polynomial contains a variable. The variable is an alphabet, depends on what you want to use. But in most cases, we use x. Sometimes you can say the variable to be y. Variable is something that takes different value. The value is not constant, it changes. Is that okay? So we are going to define our polynomial here in terms of the variable x. Does that make sense, right? So we'll be consistent with the use of x here. So let's go. A polynomial is an expression in x such that the powers of x are arranged either in descending, that is decreasing form, or ascending, that is increasing order. That's simply what a polynomial is. But there are some things you should know about a polynomial. We're talking about the powers that are arranged in increasing or decreasing order. There's something you should know about the powers. We're going to talk about that when we explain this part of the notes. Is that okay? The general form a polynomial can take is what you have on the board here. So we can refer to the polynomial as a function of x. This px here is read as a function of x. P of x. Is that okay? The p doesn't represent a function of. Sometimes you see it as f of x. I can choose to use h of x. There is no rule that it must be p of x. Is that okay? So it's generally given as ax raised to the power n plus bx raised to the power n minus 1 plus cx raised to the power n minus 2. You can also continue plus dx raised to the power n minus 3 continuously until you get to a constant that does not contain x anymore. I chose to use k for the constant. Now take note of something here. If I want to force x to enter here as a multiplier of k, it will be kx raised to the power 0. So one can say, yes, this is a constant, it is not multiplied by the variable x, but okay, I want to force x to enter there, then it will be k times x raised to the power 0. You know, a variable raised to the power 0 will give you 1. So if I say this k times x raised to the power 0, just like I explained here in the note, are you getting me? If I say this k times x raised to the power 0, x raised to the power 0 is 1. 1 times k will still give you that constant. Is that okay? So it's maintained. n minus 1, n minus 2, and the rest are powers of the variable x as given in the polynomial expression. Now, let us define the degree of a polynomial, because that's one of the very important things you should know when studying polynomial. What is the degree of a polynomial? Simply put, it is the highest power of x, of the variable, as given in the polynomial expression. And if we come back to this general form given here, you notice that the highest power of x here is n. Because as you move on, the power of n starts decreasing one by one. Is that so? Okay, so the highest power here is what? N. So we can say that this general expression is a polynomial of degree n. So for example, if this is something like 5x raised to the power 4 plus 2x raised to the power 3 minus 3x, for example, then the highest degree will be what? 4. That is the degree of the polynomial will be 4, because the highest power of x in what I just stated is what? 4. What should we know about the degree of a polynomial and even the powers of x, of the variable in the given polynomial expression? What should we know about it? Now you listen to this, we'll have it on the board here, under the notes. The first and most important is that the degree of a polynomial n must be a positive integer. Integer is a whole number, either positive or what, negative. So if I have something like minus 3, minus 5, it's also an integer. If I have 3, 2, 7, it's also integer. So positive or what, negative. But the powers of x, the powers of the variable in a given polynomial expression must be positive whole number. Take note of that. It can never, look at it, must not be a fraction, and it must not be a negative number. In the next video, we're going to use this idea to identify expressions that are polynomial and those that are not polynomial. In this video, we've got these questions on board, right? 2 of them. The first question, we have to identify the polynomial and their degrees. Then the second question, which can be considered a polynomial? So I have this expression here, which one can you consider to be a polynomial? If you see, it's not all about the simple expression we introduced earlier. So just looking at these, which ones can you call a polynomial? Alright, we'll come to question number 2. Let's first look at question number 1, where we have to identify the polynomial and their degree. So we'll start. Answers. So number 1. Look at this expression a, x squared plus 5x minus 3. That is a polynomial. So if you look at the highest power, there is 2. When you move and you have this as power 1, then this here, x raised to the power 0, if you still want to put x there. So okay, that's 3 times x raised to the power 0. So it's a polynomial because the power is a whole number, you can see that, and it's also a positive integer. So I'll write a, which is x squared plus 5x minus 3, is a polynomial of degree. Now what will you say about the degree? The highest power of x in this expression is 2, so it is of degree 2. That is actually a quadratic expression, is that not so? So what have you learned? A quadratic expression is a polynomial of degree what? 2. Alright, now let's look at the next one, b. So let's see. b, x raised to the power 5, then minus x raised to the power 3 divided by 2, then plus 6x is a polynomial of degree. The highest power of x here is 5, so of degree 5. This is a polynomial of degree 5. Why is this actually a polynomial? It's a polynomial. For you to define it, simply go and check the powers. Is that okay? Check the powers. Is the power in positive integer or negative integer? To look at this is x raised to the power 5, then there is x raised to the power 3. There is no x raised to the power 4 there. You commit no crime. Alright, the reason why x raised to the power 4 is not there simply means that it is 0 times x raised to the power 4. 0 times anything disappears. It's 0. Is that okay? Fine. Then here you notice that the power is what? Power 1. The powers are positive integers. So that's the point. Okay, now let us look at C and D. C, x raised to the power 4 plus 2 x raised to the power 3 plus square root x squared plus 1, then plus 3. Not a polynomial. Why? What's the reason? Because of square root x squared plus 1. You see, this square root of x squared plus 1 is the same as writing x squared plus 1, everything raised to the power half. Square root means raised to the power of what? 1/2. That's 1 over 2. And you know that the powers of the variable is not expected to be what? A fraction. It's not also expected to be a negative integer if it must be a polynomial. So this is why this expression is not a polynomial. Then D, let's look at it. 5 exponential 2x plus x squared minus x plus 3, not a polynomial because of the mix-up of the exponential base and x base. You see, you can't have two different functions as base in a given polynomial expression. It's not that. The base is an exponential function, exponential to x. Then the base there you can see are x terms. It's not possible. That mix-up is not allowed. It's either everything is exponential base or everything is x base. Then you now check the powers to know whether it's a polynomial or not. Okay, so we've identified those that are polynomials and those that are not. We should take a short break. When we're back from the break, then we'll look at the second question. Very important, okay? You are welcome from the short break. Now let us look at question number 2, where we are to identify the expression here that can be considered to be a polynomial. You see, if you look at expression of this kind, you might just be like, wow, this doesn't look like what I know about polynomial expressions. I can see x raised to the power this, x raised to the power that. But the truth is, there are some functions that might be combined. That's the same functions. Are you getting me? The basis must be the same function. That they might be combined in such a way that their powers are written either in decreasing or increasing order. One can formulate a polynomial from there. It's possible. In fact, you're going to encounter such in the study of logarithm. You're going to encounter that. In the study of indicial equation, you're also going to encounter that. So I had to introduce it here so that once we encounter them in those topics, it wouldn't really be a new concept anymore. As in, we would have gotten a background knowledge. So, question number 2. The first one, A, we have exponential 3x squared, then plus 2 exponential 3x plus 5 is a polynomial. An exponential base function. Because the base there is exponential, all of them is exponential. Then look at something. Having identified that this is exponential, and take note, the powers of the exponential must be the same. That's why you have exponential 3x, exponential 3x. This 5 is actually carrying exponential 3x bracket raised to the power 0. This part is actually bearing 5 exponential 3x bracket raised to the power 0. So now, having identified that the bases are exactly the same, you can see exponential 3x, exponential 3x. Then look at your powers. I've also told you this is exponential 3x, but the power is 0. Look at the powers. The power of this exponential 3x is 2. Then look at this one. The power of exponential 3x here is 1. This is exponential 3x, all raised to power 1. Is that okay? And then I've explained that this 5 standing alone is the same as 5 exponential 3x, all raised to power 0, because I had to write it in exponential base form, knowing that these ones are exponential 3 base form. Is that okay? That's exponential 3x. You see what I did there, right? Good. Let us go to the second one. The second one is exponential 3x raised to the power 2. Please, before I move on to, with this, if you work on this, we can call exponential 3x, we can say let it be equal to p. We can say let it be equal to y. Now if I say let exponential 3x be equal to p, this will become p raised to the power 2 plus 2 times p raised to the power 1, then plus 5. It's like 5p raised to the power 0. P raised to the power 0 give you 1, 1 times 5 give you 5. Am I communicating? Correct. Now let's go. So the second one, you see clearly that this second one is not a polynomial expression. You can't consider it as polynomial. So I'm going to write not a polynomial. Not a polynomial. Now what's our reason? Because of mixed up base. Mixed up base. You've explained something like this for question number 1 previously when we treated this fourth expression. So you have, look at this, an exponential function base. Then along the line, it is true, this is raised to power 2 here, this is raised to power 1 here. But look at the base here, the variable is x, no longer exponential. So you cannot have this mix up of different functions as base. Okay, so we move on to the third one, sine cube x, sine cube x. This sine cube x is still written as sine x all raised to power 3. Is that okay? That's the meaning of that. So sine cube x plus 2 sine square x minus 4 sine x plus 2 is a polynomial. You would agree with me? Following the explanation I gave for the first two here, is a polynomial. Now it's a polynomial in trigonometric base function. Base function. The trig function there is sine. Now if you look at this, I've told you this can be written as sine x all raised to power 3, 2 times sine x all raised to power 2, minus 4 times sine x raised to power 1. Then this 2 is the same as 2 times sine x all raised to power what? 0. Does that make sense, right? So you notice that the bases are all the same. All the bases are sine x, sine x, sine x, sine x. Does that make sense? Then now look at the powers. You now notice that the power is positive integers. Alright, it's positive whole numbers decreasing from 3 to 2 to 1 to 0. The highest degree here is degree 3. So we can actually convert this to a polynomial expression of degree 3. Let's take a short break. When we come back, we'll analyze this as another polynomial expression in this question 2. And now we want to look at the last expression here. Is that okay? We have to find out whether it can be considered as a polynomial or not. Okay, let's look at this. So I'll write for 2d, what we have there is 2 raised to the power 2x, then minus 3 brackets 2 raised to the power x minus 4. Now let me show you something quickly. Let's look at something. Do you know that this can be written as, this is the same as 2. Now what do I want to do? I want to shift this 2 backward like this and then this x forward. So it's going to be 2 raised to the power x. Of course, you know the power is actually 2 times x. So it's the same as x times 2. The point here represents times. Is that okay? I've done the shifting here. I've done the shift. And if I shift that, I can actually put this in bracket like this. I can actually put it in bracket this way. So that this will now be minus 3, 2 raised to the power x, then minus this 4. Take note of something now. You notice that each of the terms here have the same base. And the base there is 2 raised to the power x. 2 raised to the power x. In fact, this 4 here is the same as 4 times 2 raised to the power x, everything raised to the power 0. Remember, a term raised to the power 0 will give you 1. Then 1 times the 4, you maintain this at minus 4 there. Does that make sense, right? So I commit no crime. I am still mathematically consistent if I say that this is 4 times 2 raised to the power x, then everything raised to the power 0. So you now notice that this expression has the same base, 2 raised to the power x. And then you notice the powers decrease. This is power 2, this is power 1, this is power 0. Therefore, 2 raised to the power 2x minus 3 times 2 raised to the power x minus 4 is a polynomial. Is a polynomial expression. Is a polynomial expression in 2 raised to the power x base. Is that okay? That is in 2 raised to the power x base or in base 2 raised to the power x. In fact, you will encounter things like this under initial equation in indices, as we will treat in this course. If I choose to call this 2 raised to the power x as maybe k now, you notice that this becomes k raised to the power 2 minus 3k. That is 3k raised to the power 1, then minus 4k raised to the power 0. K raised to the power 0 gives us what? 1. 1 times 4 gives us, that's a minus 4 here. So you see that there are some expressions that might be given to you. Looking at it directly, they may not look like polynomial, but if you look intently with the GMAT 41's eye, you will notice that that is actually a polynomial. Next video, we are going to introduce addition and subtraction of polynomial. In this video, we want to look at the operations that can be carried out on polynomial expressions. So we can add, we can subtract, we can multiply, we can divide polynomial expressions. Is that okay? We are starting with addition and subtraction of polynomials first. And to add or subtract polynomials is a simple one. All you need to do is to pick their like terms. Is that okay? You know that polynomial expression is actually an algebraic expression because we have numbers and alphabets combined there. Is that so? So they are actually algebraic expressions. So to add or subtract them, you pick the like terms and work together. terms that are unlike, you cannot add them, you cannot subtract them. Is that okay? So now the question could be, how then do we identify like terms of a polynomial? Is that so? And the answer is simple. The like terms of a polynomial is simply obtained from the powers of the variables there. Alright, so if I give you two or more different polynomials, they are like terms, you go in there, okay, which terms there have the same powers? Those terms that have the same powers are like terms. We have this example here on the board, is that okay? We have two polynomials, one is p of x, and then the other will label it as f of x. If you look at this is x raised to the power 4. If you come to this polynomial f of x, did you see any x raised to the power 4 there? No. It means that there is no like term of x raised to the power 4 in f of x. In fact, you can say it's 0. Because here, if you want to fix in x raised to the power 4 in f of x here, it's going to appear as 0 times x raised to the power 4. Is that okay? That is why there is no x raised to the power 4 here. Because 0 times any number will give you 0, so it goes up. Alright, so we can rightly say that x raised to the power 4 does not have any like term here. Now let us look at this x raised to the power 3. You notice that I'm not interested in the coefficient, the number that is multiplying them. Is that so? I'm not interested in it, in getting my like terms. So x raised to the power 3. You come over here, do you have x raised to the power 3 there? Yes. That's minus x raised to the power 3. Therefore, this plus 3x raised to the power 3 and minus x raised to the power 3 are like terms. What about terms in x raised to the power 2? This is plus 5x raised to the power 2 from p of x. This is minus x squared. So you look at x raised to the power 2, x raised to the power 2. So this term and this term are like terms. So you can see that. The same thing, the constant, these ones without x, minus 6 and plus 1. Alright, now observe, I've stated x raised to the power 4 does not have any like term here. Then notice something, 2x in f of x does not have any like term in p of x because there is no x raised to the power 1 in p of x. So this is how you identify your like terms. Is that okay? Please take note of this, go through them, go through this short note here. When you are working with addition and subtraction, as in fact, generally operations with a polynomial expression, you want to respect the signs and board marks. We have this question and the board wants to look at. If p of x is equal to 3x raised to the power 3 plus 5x raised to the power 2 minus x plus 2, and h of x equal to x cubed minus x squared minus 2, find a p of x plus h of x, b h of x plus p of x minus h of x. Now how do we approach this question? It's a simple one. Alright, so to solve, we have a solution here. These were the polynomials given to us, I just had to bring them out. The first part of the question A, we have to find p of x plus h of x. Now how do we handle this? Remember, you take them like term by like term, you group and then you add. So the like terms we judge based on the power of x. Here you have x raised to the power 3, that's the highest power of x here. And then you notice that in this h of x, you also have x raised to the power 3. So these and these are like terms. We can add them up. So I'm going to say 3x raised to the power 3, then plus, let me write those terms in h of x with red marker. Is that okay? So that's going to be plus x raised to the power 3. Then the next term plus open brackets. We now check for x raised to the power 2 terms. Is that okay? Here we have x raised to the power 2 in p of x, the quotient is 5. Then here we have x raised to the power 2 in h of x, the quotient is minus 1. So you pick both of them. I'm going to write this is 5x raised to the power 2, then plus, good. Coming to this, remember this is minus. So you want to pick that minus x squared. I already stated in the previous video that you want to respect signs so you don't get into trouble. Is that okay? Then we look at terms in x raised to the power 1. I'll come to p of x. Do I have x raised to the power 1 term there? Correct. That is minus x. So I'm going to write minus x. I will add it to the x raised to the power 1 term in h of x. So let's see if we have the like term there. There is no x raised to the power 1 term. Is that okay? So if I like, I can put plus 0. If I don't like, I would remove it because any term plus 0 is that same term. Lastly, we pick terms that do not bear x. That is constant. Then from p of x, you have it to be plus 2, which is 2. And then from h of x, you have it to be minus 2. So you put minus 2. You know, plus 2 is still the same as writing 2. I don't know if you're getting it right. But if it's minus 2, you must show the sign. We can now conclude that p of x plus h of x is now equal to, you come over here, 3x raised to the power 3 plus x raised to the power 3. How do you work around this quickly? Pick their like terms first. This is 3 as the coefficient rather. Pick their coefficient. And this is invisible 1 as coefficient. So 3 plus 1 will give us 4. To be 4, then you pick the common term, x raised to the power 3. Is that okay? Come over to this. This is 5x squared plus minus x squared. The coefficient here is 5. The coefficient here is minus 1. 5 minus 1. You know, plus times minus will give you minus. 5 minus 1 will give us positive 4. Then pick the common terms. Then you come over here. This is minus x plus 0, which is plus. Okay, that is going to be minus x. Minus x. Minus x plus 0 is minus x. Then plus times minus, you maintain that minus. 2 minus 2 is 0, so it goes off. Therefore, this is the result of the addition. Now, we want to look at the second part of the question. That is B part. That B part, we have to evaluate h of x plus p of x, then minus h of x. Is that okay? Without solving this, you know that the answer is equal to p of x. What we are going to get, the answer is going to be this polynomial. It's very clear from here, you can see, because here h of x minus h of x will give you 0. I hope you know that, right? Then you'll be left with what? P of x, which is your result. So our answer is actually 3x raised to the power 3 plus 5x squared minus x plus 2. But for clarity purposes, let's just solve it. Is that okay? So this is going to be equal to now we will pick our h of x plus p of x. H of x plus p of x we solve is equal to this polynomial there, is that so? So I'll write 4x cubed plus 4x squared minus x. This is our h of x plus p of x. There's going to be minus h of x. And h of x is what? H of x is giving us x cubed minus x squared minus 2. So we're going to pick them like term by like term and then we'll work around it. Is that okay? So look at, we have x raised to the power 3 and the highest power in this term here is x raised to the power 3. So we can pick it, which is 4x raised to the power 3. Then we'll come over here. Is that okay? You know, if you use this minus to open up these brackets, these signs will change. In fact, let me write it here. This is the same as minus x cubed plus x squared plus 2 by opening up the bracket with this minus sign. Is that okay? Good. So coming over here, we have x raised to the power 3 as a like term, but it's minus. So I'm going to write minus x raised to the power 3. It's like term, you pick that. Then plus, look for x raised to the power 2 term. Is that okay? Here we have 4x raised to the power 2. Now we'll come over here and pick its like term. Do we have x raised to the power 2 there? Yes, that is plus x raised to the power 2. And then we'll come over here, we have x raised to the power 1 term. We're going to pick it plus, that is minus x. Now we'll come over here, do we have an x raised to the power 1 term there? No. So it's going to be plus 0, plus 0. So I choose to use different markers so that you see, we'll pick from this time with blue marker, the other time with red marker. It's not a rule. So don't go and write with different colors of pen. Alright, just for you to see what we're doing when I'm picking them. Then plus, lastly, we look at terms that do not get x at all, which is constant term. Here, is there any constant term here? No. So you're going to write 0. Then you come over here, is there any constant term in this h of x here? That's going to be plus 2. Now we are done, we can now simplify. This is 4 minus 1, then you pick the x cubed. Or is it 4x cubed minus x cubed, which is going to give us 3x cubed. Come over here, plus 4 plus the quotient 1 here will give us 5, then x squared. 5x squared. Then here is going to be minus x, and then this is going to be plus 2. You see, we've gotten our answer. Compare this thing with the value of p of x, the polynomial that you see that they are equal. So this is how you handle addition and subtraction of polynomials. It's a simple one. The next video, we're going to look at multiplications of polynomial. This is GMAT 41. You are welcome to our elementary mathematics class. In the previous class, we treated addition and subtraction of polynomial expressions where we stated that to do that, we work with their like terms. You add and subtract like terms. Where like terms with polynomial deals with those terms that have the same powers. In this video, we are introducing multiplication of polynomial expressions. How do we multiply polynomial expressions? To move on into what we have here on the board as a note that will guide us, I'd like to quickly remind us of something we do under algebraic expansion. Imagine that you're given x plus 5 and then to multiply with, let's say, x raised to the power 2 plus 2x minus 1. You would recall that to do a multiplication of this kind, usually we pick one of the terms here, use to multiply all the terms in this bracket, then come back again, pick the second term, use to multiply all the terms in the other bracket. Is that not so? Eventually, we might arrive at the correct answer at the end of everything, if, of course, there is no mistake along the line. Now, when you are dealing with polynomials of higher degrees, let's say from degree 3 and above, multiplying, going through this process, whereby you use each of the terms here to multiply all the terms here, and if you get it right, might become cumbersome, tedious to work with. And that is why in this video we introduce a very wonderful concept of how to multiply polynomial expressions faster. We have this note on the board that is going to guide us. But the key point is this: to multiply polynomial expressions faster, we pick terms whose product, whose multiplication will give us the same degree. That is, will give us the same power. And then doing this multiplication in order of decreasing power. I'm going to underline the key term or the key statement on the board here so that while you go through that, you'll be guided by it. Look at it, it's faster to pick terms whose product gives the same degree, doing so in decreasing order of what? Powers. How do we actually do this? Let's consider this example we have on the board. Just imagine you're given this polynomial x raised to the power 3 minus x raised to the power 2 plus x plus 3 to multiply by x squared plus 3x minus 2. Now, the first and most important thing you need to do is to ask yourself, which term from this polynomial will I multiply by a term in this polynomial to get the highest power of your expansion? This is the answer to that. To get the highest power of any polynomial multiplication, you are expected to multiply the highest degree in one of the polynomial by the highest degree in the other polynomial. For instance, x raised to power 3 here is the highest degree of this polynomial. This is a polynomial of degree 3. And then x raised to power 2 is the highest degree in this polynomial. This is a polynomial of degree 2. Now, if you multiply x raised to power 3 by x raised to power 2, using law of indices, you pick one of the x and then add the powers, right? So eventually, you're going to get x raised to power 5. It means that to multiply these two polynomials, the highest power or degree of the result you're going to get will be x raised to power 5. Once you're able to identify the highest degree of your expansion, you are now set to carry out your multiplication fully. The next would be to pick terms, which if you multiply them, you will get x raised to power 4. The first was the highest power, and it gave us x raised to power 5. So in decreasing order of their powers, the next will be x raised to power what? 4. Now just look at this. You notice if you pick x raised to power 3 and multiply by this 3x here, and then x raised to power 2 and this x raised to power 2, you're going to produce x raised to power 4. So you see how you pick them, right? Then after that, you now look at those that will give you x raised to power 3, x raised to power 2, x raised to power 1, and then the constant term. Very wonderful, right? You see, this process helps us to be fast with our multiplication, and then to have small terms rather than getting a very large expression as could be encountered if we are to expand fully in this format. In the next video, we're going to pick questions and then see how we apply this procedure about picking terms that will give us the same power when being multiplied. We have this question on the board here. We're given this polynomial f of x raised to power 2 plus 3x minus 2, and then this polynomial p of x equal to x raised to power 3 minus x raised to power 2 plus x plus 3. We have to evaluate the product f of x times p of x. Is that okay? So we're multiplying these two polynomials. So what do? Okay, look at our solution. We want to work on this now. I have to bring out the polynomials first, and then we have our f of x times p of x. Now you recall that we stated that the first thing we have to do is to get the product that will give us the highest power of the expansion. And we stated from the previous video that to do this, we pick the highest degree in f of x, pick the highest degree in p of x, and then multiply the two terms, the two highest degrees. Now if you do that, x raised to power 2 times x raised to power 3 will give us what? To give us x raised to power 5. You know how we get that, right? You are multiplying the same base. So you pick one of the x, and then you add the powers. Multiplication law of indices. Very important place. Be guided by that when you are doing multiplication of polynomials. Now we've gotten the highest degree of this expansion. It therefore means we now need to check for x raised to power 4 term, x raised to power 3, x raised to power 2, x raised to power 1, and possibly the constant. Is that not so? So let us go for the terms, which if we multiply them, we'll get x raised to power 4. So I'll put plus, open bracket, we go. I'll pick x raised to power 2 from here and ask myself, what will I use to multiply? Which term will I use to multiply here to get x raised to power 4? I'm looking at this, x raised to power 2 times minus x raised to power 2 will give us x raised to power 4. Because if you add their powers, 2 plus 2 will give us 4. Is that not so? So let's do that. X raised to power 2 times minus x raised to power 2 will give us minus x raised to power 4. Remember, plus times minus will give us minus. I already stated in the previous class that when you are dealing with this, please don't play with your signs. Very, very important. Your plus, your minus, they are extremely important. Okay, now we are done with x raised to power 2, multiplying this to give us x raised to power 4. Let us now still go ahead and then look at this 3x. Can it multiply anything here to give us x raised to power 4 term? And I can see that that is possible. Look at this. 3x raised to power 1 multiplies this x raised to power 3 will give us x raised to power 4 term. Is that okay? This is x raised to power 1, this is x raised to power 3. That 1 plus 3 will give us what? 4. So 3x times x raised to power 3 will give us x raised to power 4 term. Let's do that. 3x times this will give us plus 3x raised to power 4. Take this is plus, this is plus. So if we multiply, we'll still get plus. And then I will now ask myself, the next term is minus 2. Can this minus 2 multiply any term here to give us x raised to power 4? And the answer is no for what I'm saying. The highest thing that this minus 2 can multiply here to give us a higher degree is x raised to power 3. It means that this minus 2 cannot produce x raised to power 4. Therefore, we are done with x raised to power 4 term. We close the bracket and add, seek for x raised to power 3 term. Now, are we ready? We'll go back again, pick your x raised to power 2. Ask yourself, what will you use to multiply here to get x raised to power 3? I'm going to be fast this time now, believing that you've gotten the idea from what I explained here. This x squared multiplies this x will produce x raised to power 3. This is power 2, this is power 1. So if you add the powers, you get power what? 3. Therefore, we'll go to multiplying x squared by this x, and that will give us x raised to power 3. Next, I'll pick 3x here. This 3x and multiply this minus x squared to give us x raised to power 3 term. Because this is 3x raised to power 1. If that power 1, if you add it to this power 2, you get power 3. So let's do that. Plus 3x times minus x squared will give us minus 3x raised to power 3. Then we'll pick this minus 2 and ask ourselves, can it multiply any term here to give us x raised to power 3? And the answer to that is yes. If it multiplies this x raised to power 3, it's going to produce x raised to power 3 terms. So let's do that. Minus 2 times plus x raised to power 3 would give us minus 2x raised to power 3. And so we are done with x raised to power 3 terms. We now seek for x raised to power 2. Let's do this. This x raised to power 2 can multiply this 3 to produce 3x raised to power 2. We are done with this. We move to this. 3x here can multiply this x to give us x raised to power 2 term. You know, this is x raised to power 1, this is x raised to power 1. If you add 1 plus 1, you get 2. So 3x times this x would give us plus 3x raised to power 2. You know, it's plus because this is positive sign and this is positive sign. Then we pick this term, now minus 2. Minus 2 can multiply this minus x squared to give us x raised to power 2 term. This is minus, this is minus. So minus 2 times minus x squared, we change to plus 2x raised to power 2. We are done with that. The next, we seek for x raised to power 1 term. Can this x raised to power 2 multiply anything here and produce x raised to power 1? It's not done because these are positive terms already, positive powers. And this is x raised to power 2 already. The power here is already greater than 1. So you can't use it to multiply anything here to get x raised to power 1. So you forget about that. This is 3x. What can you use 3x to multiply here to get x raised to power 1? 3x can multiply this x to give us x raised to power 1. And if you do that, you're going to get 9x. You're going to get 9x. Then lastly, minus 2. Minus 2 can multiply this x here to give us minus 2x. Minus 2x. Then the last expansion is the constant term. Terms that you multiply and there will be no x. And that can only happen when you multiply the constants themselves. So minus 2 times plus 3 will give us minus 6. We are done with the multiplication, so we can now simplify by adding or subtracting like terms. And good enough, the like terms are already in brackets. Is that okay? Now to add and subtract, recall we've done that from our previous class already. So let's go. This is x raised to power 5. There's no like term to read, so you have x raised to power 5 there. Come over here, this is minus x raised to power 4 plus 3x raised to power 4. Already we've done addition and subtraction, but let me just quickly show you what we do there. X raised to power 4 is common to both, is that not so? So pick their coefficient. This is minus 1 as a coefficient, as a multiplier of x raised to power 4. This is plus 3. Minus 1 plus 3 will give us what? To give us plus 2, is that not so? So that's going to be plus 2 raised to power 1, that is plus 2x raised to power 4. Come to this is x raised to power 3 minus 3x raised to power 3. We'll get minus 2x raised to power 3 here. That minus 2x raised to power 3 minus 2x raised to power 3 again will give us minus 4x raised to power 3. Come to this term, this is 3x raised to power 2 plus 3x raised to power 2. You get 6x raised to power 2 here. Add it to these 2x raised to power 2, that will give us plus 8x raised to power 2. Then this will give us plus 7x. Then plus times minus will give us minus 6. And this is how we solve this problem. Pretty simple.